And then with the screen share. Okay, so for today's session, I thought we'd look at the following task. Um, and what we're looking at is a curve, and we're starting like with a bit of a very, very simple example. The curve RT, which is t square 0. And I want you to find two different surfaces in three-dimensional space which contain this curve. And afterwards, we're also going to sketch them, but for the time being, just find two different surfaces containing the curve. If you have any results or if you have any questions about that, just post them in the comments, and otherwise just go ahead, give it a try for a couple of minutes. Okay. Does anyone have any idea for like one surface maybe that contains this curve? Any candidate? Okay, there's the first candidate. Y is equal to x squared. Do we have a second candidate? Different surface maybe that also contains this curve. Okay. So let's first take a look at what this actually looks like in three-dimensional space. So if we plot the whole thing, then we have our x-axis, y, and our z. And now if we plot our r of t, then of course, this is just our standard parabola in the xy plane. So we get something like this, right? So let's plot that. Okay, so this graph here, this is r of t, walking in this direction. And now we want to find surfaces containing this curve. And of course, a surface means something, I mean, that is not just a line, but something that looks like a plane or something like that. And there are now there are, of course, many surfaces that contain this curve. So if we just look at it, I mean, there's many different ways. So for example, we can just let the curve stay in the xy plane, so where the z coordinate is 0, and just move it up and down, right? This would give us a surface if we just moved it up and down along the y-axis. And the surface that we would get is then, of course, just the xy plane. So the actually the easiest, actually let's look at this one. The easiest plane, or the easiest surface, is just the one that is given by z equal to 0, which is the whole, maybe let's just color this. Right, continue this, but this is the easiest surface probably containing our curve. Of course, there's also one other one that was already in the comments twice, once more, a bit more conveniently written down, the other one. And this is if we just move our curve up and down, right? So if we move it up and down, we of course also get a surface. And of course, it still contains, let's just move it a bit more up. And of course, it also contains our original curve. And that is still very easy to write down. I mean, of course, we didn't need to move it just up and down. We could have also moved the curve in a bit of a diagonal, or we could have moved it like in a very funny way around space, and we would also get a curve, a surface that contains our curve. But that would be pretty annoying to write down. We just want to find two different surfaces. We already have one. We should move this away. And now we take a look at the other one. Well, let's first sketch it. And this would be pretty much the outside of our surface, and then looking inward. Okay, let's go for purple. We would see something like this, right? Actually, no. Let's just try this part. Okay, so this would also be a surface that contains our curve, and of course continued up and down for infinity. And that is maybe the second easiest one. And that is just given by y is y is equal. Okay, no, different color. We were using red. Y is equal to x squared, and z is then arbitrary, which we usually don't write, but just to make it absolutely clear, this is what happens. We have this this parabola, and then we move it up and down. How do we come up with this? the general idea is that we try to find relations between the components and then just start ignoring the third parameter. So for example, if we tried to find a relation between the first two parameters, then we would see that if we take the first component and square it, we get the second one. So this is precisely y is equal to x squared. And then we just don't care about the z coordinate at all anymore, because if that is arbitrary, then no matter what happens in the z coordinate, of course, our curve has to be contained in this surface. Now, after we've seen this kind of pretty simple example, I'd like us to move on to one that is a bit more complicated. And this time we're looking at the following curve, which is given by t squared logarithm of t and 1 over t. And I want you to find 3 different surfaces that contain this curve. And afterwards, we are again going to sketch them. But first of all, take, let's say, 3 or 4 minutes and work out 3 different surfaces that contain this curve. And again, if you have any kind of idea or result or question, either unmute yourself, post them in the comments. I'm here.
Doctor, will we have a surface for each like for the x-axis equal to 0, that's one surface, and then y equal to 0, and then z equal to 0?
Sorry, you got to repeat that. I didn't quite get that.
Will we have a different surface when each of the coordinates are 0? Like when we have x equal to 0 and y and z have values, and then when y is...
No, continue, sorry. To break you off.
And then when y is equal to 0, we will have a surface where x and z exists, and then z equal to 0.
Ah, okay. So let's take a look at that. So you are considering, I think, the following surface. So let's take a look at the surface x equal to 0, right? That was the first surface you wanted to take a look at. So if we want to find the surface where x is equal to 0, then this is just the xy plane, right? Of course, continued in each direction. This is definitely one surface, but this particular surface does not contain the whole curve. Why? Well, if, for example, we look at the value at t equal to 1, then we have something like 1 something something. So we have a point that is somewhere over here, which is not contained anymore in our plane where x is equal to 0. We might have, of course, an intersection between this curve and this plane, but the curve is in this case not going to be contained in this plane, right? The curve, I don't know, looks something, actually I have no idea what it looks like, and I'm scared to try to sketch it. Yeah. Is that what you wanted to do, or did I misunderstand you?
No, I understood now. Thank you, Doctor.
Okay, you're welcome. Okay, any ideas for a surface or two or maybe three that would contain this curve? Okay, if that's not the case, I'll just tell you how I would approach this problem. So the idea is that, again, as I said, we try to find a relationship between any two of the components, or these two, and then we plot the surface that we get via this relation. And if we just take this relation, then we would move it up and down because we have an arbitrary z coordinate. Or maybe we would move it, if we have a relation between these two, we would move it in x direction to front. And if we have a relation between these two, we would just move it in the y direction arbitrarily. Okay, so let's try to find relationships between any two of the components. And maybe the easiest one that we directly see is a relationship between the x coordinate and the z coordinate. So if we have a point x, y, z on our curve, then if we square the z component, right, then we get 1 over t squared. And then we take 1 over z squared, that gives us t squared. So this is equal to x. So if we take x equal to 1 over z squared and y arbitrary, then this is a surface containing our curve, right? Because every point on this curve satisfies this. And yeah, so it's contained, and this is definitely a surface. This is definitely not just one-dimensional, it's two-dimensional, three-dimensional space. Similarly, we can look at, for example, the relationship between these two. Well, what's the relationship? Again, if x, y, z is a point on the curve, then how do we get from one to the other? Well, if we wanted to get y out of x, this would be annoying because first you would have to take a square root and then we would take a logarithm, and that just doesn't sound great. But what we can do instead is we can take the y coordinate, take e to the y coordinate, and then square the whole thing, and then we get the x coordinate. So x is equal to e to the y squared, so this is just e to the 2y. And similarly, we can find relation between the last two. So how, well, getting from 1 over t to ln t is inverting and then taking a logarithm, which is again annoying and horrible to plot, but we can also go the other way around. So if we just take e to the ln of t, this gives us t. And if we want to get 1 over t, of course, we just take e to the minus ln of t. So x, y, z is a point on the curve, then z is equal to e to the minus y. And okay, we should finish the sentences. So we have this relation between the x and the y coordinate. So again, x is equal to each of the two y, z arbitrary is a surface containing our curve. And here, so z is equal to e to the minus y with x arbitrary. With x arbitrary is another surface containing our curve. So the question is there was a question, is y equal to the logarithm of z? Is that correct? Well, not quite, because if you take the logarithm of this thing, you get minus this thing. But you will see in a bit that it actually doesn't, apart from the sign error. Yes, of course, that's also correct. The only thing that is a bit annoying then is if you start working with logarithms, you know, you have to take care that the z coordinate is always positive, and we can just make this a bit simpler by always using the functions that are always defined, like taking e to the something instead of going the other way around, where we're taking logarithms. But in theory, yes, absolutely, you can also do it like that. And you would just get a different surface, one that doesn't move, one where z is always positive. Okay, so now let's get to sketching these three surfaces, which, as you can, or as you probably know, is not my favorite part. But how do we go about this? So let's first sketch x is equal to 1 over z squared. And the first thing we do to get, or what I would do to get a good idea of what I should plot, is I first draw just in two-dimensional space, and then we transfer to our three-dimensional coordinate system and get the actual surface. So we first want to have, a very, very rough sketch. And if we write it down like this, this looks like x is a function of z. So, and we already know this function. So what I would do is I would sketch it like this, even though, of course, this is very unusual having an x coordinate and a z coordinate here. But if we do it like this, we can sketch it, and we know what this function looks like, right? So as z approaches 0, of course, we get something that is very, very large. It's always positive because we have a z square. So what we get is something like this. And for z negative, we just get pretty much the same thing, just on the other side, okay? Now, this is what this looks like just in two-dimensional space, but we wanted a surface, so we now need to transfer it to three-dimensional space. So let's get our 3D coordinate system. Now this is x, this is y, this is z. And this image now has to appear in this plane, right? Just regrettably a bit twisted and turned because now it goes in different directions. But that's not too difficult. I mean, we see that as z approaches 0, we get very, very large values of x. So we know that the shape is going to be something like this, and we know it's asymmetrical. So if we just transform this plot into this coordinate system, what we get should be something along the lines of this. But this, of course, is still not a surface, right? This is just this is not the surface as x is equal to 1 over z squared. This is the plot of x, or the curve x is equal to 1 over z squared and y is equal to 0. So to make the surface out of it, yes?
Why is z negative?
We can, I mean, in this, if we view it as a function, we can put in arbitrary values of z, right?
Okay.
So this is the we can't get negative values for x, right? This is why it's not in these quadrants. But if we just take a look at this surface described by x is equal to 1 over z squared, then of course we can plug in any value for z that we like.
Thank you, doctor.
You are welcome. Okay. Now to make the surface out of it, we're just gonna take the curve and just move it to the left and right, and that was going to give us a surface. So we're gonna do this. And I'm very grateful for using technology for that. So let's maybe put it like this. And then just, yeah. So this is one part of the surface. Of course, extended up and left and right and so on. And then we also have the other part of the surface, which we can now view from, well, basically two sides. So we have pretty much this part. And this part. Okay, I hope you can get an idea of what it's supposed to look like. But the idea, of course, was just to take the curve and move it left and right, and then this gives us a surface. And this surface over here is going to contain the original curve that we started with. Okay, let's go to the second one. The second one is this relation, x is equal to e to the 2y. Again, we're going to start with a plot in 2D. So this again looks like x is a function of y. So just to get the good idea what the shape's going to be like, we're going to label it like this, even though again that is very unusual. And then, well, what does it look like? Well, I'm not able to really show you what the difference between e to the 2y or e to the y is, because for me it's all going to look like the same exponential function. But the only thing we know is that when y is equal to 0, we get the point 1 over there. If we have very negative values, it goes like this, and afterwards it's like, grows very rapidly. So it's standard exponential function. And now we need to transfer this into our three-dimensional coordinate system. So x, y, and z. And when we transfer it, we start with z equal to 0. So we're just going to try to put this plot into this xy plane. And this, of course, is now just, well, pretty much mirrored, right? Here, x goes in this direction, and here, x goes in this direction. So what we do is we have here our point where y is equal to 0, x is equal to 1, and z is equal to 1. And then we have something like this, I guess. Well, I don't think it grows rapidly enough. No, it doesn't grow rapidly enough. No, still not good. Sorry. Yeah, that I think looks more like it. Is this right? Looks right. Yeah. Okay, and what we do then is, again, we just move it up and down. And we get the following surface. So on the inside, kind of looks like this. And here we have a bit of an outside view of that thing, I guess. Yeah, that doesn't look particularly pretty, I'm sorry, but I hope you get the idea of what the surface is supposed to look like. We also have one last surface to look at, which was this one. Z is equal to e to the minus y, and now x is arbitrary. So let's try this one. Again, oh, what is that? Okay. We start with the 2D coordinate system. And now we need to plot this thing. Well, this is pretty much the standard exponential function, just with a minus y and plus I, so we can just imagine it as being, you know, the other way around, mirrored at the, in this case, this axis. So we have a bit of this point, and then we have very rapid growth over here, and then it goes to 0 over here. And now we need to put it in a in a 3D coordinate system. In this case, this is very easy because here we see that the coordinate system here, the 2D one, is exactly this coordinate system, so we can just copy this. And now we need to move this curve in the x direction. Right, move it a bit in the x direction, move it a bit in the other x direction. And we get a surface. Okay, is clear what I've done so far in this video, or in this video, in this session, sorry.
Doctor, can you please just show us for one of the axes or the surfaces, how did you find the equation?
Okay.
Yeah.
You mean this part over here?
Yeah, yes.
Okay, sorry. We had the curve given like this, okay? And now we want to find a relationship, in this case, between our x coordinate and our z coordinate. And we want to express one as the other, or by the other. So how can we do this? Well, we know that, if x, y, z is on our curve, then first of all, there exists a t such that x is equal to t square, y is equal to ln of t, and z is equal to 1 over t, right? This just means that we have a point on our curve. Now, In the first part, we're going to ignore the y component. Just try to find the relationship between the first and the third component, and then we're going to move the curve that we get over there in the y direction and get the surface. So let's forget about the y. Now we want to find relation between x and z. And they already look pretty similar, right? I mean, there's no crazy functions going on. Here we have a t square, and here we have a 1 over t. And if we square z, then we get 1 over t squared, which is almost x. So the only thing that we need to do is we need to take 1 over z squared, right? If we now just plug in the actual values, then on this side we get t squared, and on this side we get 1 over t squared, which is t squared. So this is the idea. Try to find a relationship between any two of the components that you have and try to express one as the other or by the other. Is that clear? Is it still unclear? Actually, never mind. We'll just take a look at another example, okay? I mean, we did this 3 times, so let's just go through all 3 of them again. Here for this one, I wanted to find a relationship between the first and the second coordinate here. So I want to find a relationship between t squared and the logarithm of t. And what I do to express one as the other is, well, it looks like it's going to be, for me, it looks like it's going to be easier to transform the second coordinate to get the first one. And to get t squared out of ln t, well, what I need to do is first I need to build e to the ln t. This now gives me t. And now I square it, then I get t squared, right? So this is t squared. So this whole thing is t squared, and this is precisely the x component, which then gives us, if we move it in the z direction up and down, a surface. And for the last one, I wanted to find a relation between z and y, which are these two. So again, I wondered, okay, how can I express one of them by means of the other? And again, I thought that taking logarithms is, I mean, it's possible, but I think it's a good habit to always use, you know, if you can use functions that are always defined, where you don't need to take care that something is positive or negative, just do that. So if I want to get 1 over t, if I already have the logarithm of t, well, first again, of course, I'm going to build e to the ln of t, which gives me t. But I want 1 over t, so I actually take e to the minus ln of t, which is 1 over e to the ln of t, which is 1 over t, which is precisely the third component. Is it now clear what I did?
Yes, thank you so much, Doctor.
Okay, great. Actually, we're going to test if that was clear, because I would like you to find, well, actually, let's make this, for time reasons, I would like you to find 2 different surfaces containing this curve, where the first component is 2t, the second one is e to the t, and the third one is e to the 2t. And again, for the time being, we're going to sketch them. But yeah, just think about this for a moment and see if you can find 1 or 2 surfaces that contain this curve. And if you have an idea, just put them in the comments. Okay, great. This looks pretty good. You have a couple of ideas. There was one mention that doesn't quite work, but I think that's just like a tiny little mistake. So if you want to go from what was it? You want to go from x to you want the relation between x and z, then of course you need to take the exponential function of the whole thing. Just taking the whole thing twice doesn't work. But apart from that, yes, those are very good answers. Thank you very much. I think, yes, that answered, like, if you didn't get anything so far, please give this a go. Also, try to sketch them, even though, well, at least personally, I find it annoying to sketch these things, especially in 3D. Now, there was a question, how does this work in an exam? Like all these sketching tasks, how does that work in an exam? And usually, of course, you don't like have to sketch anything yourself. All the sketching tasks will be, you will be shown a couple of different plots, a couple of different surfaces, and then something like mix and match, right? So which one of the following formulas belongs to which of the following plots? And this is how we are going to test your sketching abilities where you don't need to sketch yourself anything at all. Do you have any more questions? If that is not the case, I think we are done for today. I wish you a great weekend. Now also the lockdown is lifted. I hope you, will enjoy that. And I'll see all of you again on Sunday, hopefully. Don't forget that the first set of homework is due Saturday night. So that will be, please just don't miss the deadline, okay? And have a great weekend and talk to you soon.
Thank you.